This module will cover what are the recommended corn seeding rate ranges for Ohio production environments, how yield can be impacted by seeding rate, and how other management decisions impact seeding rate. For Ohio production, the level of yield in the environment can matter when we're making seeding rate decisions for corn hybrid production. In Ohio, high yield environments tend to respond better to high seeding rates and ultimately can produce more yield with greater final stands as compared to low yield environments. In many cases, a final stand of 34,000 plants per acre or more is beneficial in these environments. In low yield environments, lower seeding rates are typically required to achieve final stands in the range of 24,000 to 26,000 plants per acre. Again, the lower yield potential of these environments leads to less plants being needed to maximize yield on that area. The seeding rate, though, regardless of the environment, may need to be adjusted to account for anticipated loss or attrition. In general, across Ohio environments, the recommended seeding rate range is between 30,000 to 36,000 seeds per acre, with most environments doing well at a final stand of 31,000 to 32,000 plants per acre. You may need to adjust your seeding rate to reflect what your anticipated or desired final stand is. Adjusting a seeding rate for final stands can be done using the following steps. The first step is to determine what your final desired stand is. In this example, we're using 34,000 plants per acre, which is a typical stand that you might need in a high yield environment to maximize yield production. You need to next assume that there will be some level of attrition or loss of the planted seeds, either because of variability in the germination of the seed lot that's being used. There could be adverse environmental conditions, which could affect seed germination and establishment. There also could be other reasons for loss of seed. And it may be expected that the loss may be greater in low yield environments due to the increased prevalence of adverse conditions. To determine the seeding rate that's going to be needed in seeds used per acre, we can take our target final stand and divide it by 100 minus our anticipated percentage loss. In a high yield environment, a target final stand, for example, may be something like 34,000 plants per acre with an expected loss after planting of 5%. If we apply the previous formula, we arrive at a target seeding rate of 35,780 seeds per acre, which is roughly a 5.2% increase as compared to the targeted final stand. In a low yielding environment, if we were targeting a final stand of 26,000 plants per acre and anticipated attrition of 12%, we'd need to target a seeding rate of 29,550 seeds per acre, which is a 13.6% increase over our target final stand value. Once you've determined what your seeding rate should be for a given field, it's important to conduct a stand count to ensure that the seeding rate was adequate to achieve your targeted final stand. In corn, we tend to use a length of row for counting that is 17 foot 5 inches in length in a 30-inch row spacing. The reason we use this length is because when you take that, multiply it by the row width, it equates to essentially 1/1000th of an acre in area. When you're conducting a stand count, each plant within the row is counted, but you should also investigate large gaps in the row, if present, for the presence of seeds to see if it was a seed issue or potentially a planter issue. The final count value that's derived from that length of row can be multiplied by 1,000 to get the final plant stand for that area. In most cases, the stand that is counted should be equal to or less than the targeted seeding rate, given the fact we anticipate some attrition occurring in the field. In the next clip, we'll see how a stand count is conducted at roughly the V3 growth stage. Okay, so looking at our first row, we have our flag here. We're going to start counting the far row over there, and we're going to start counting. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31 plants in our first row. Whether you're seeding at 24,000 or 42,000 seeds per acre, depending on your environment, there's many factors that need to go into this decision. The reason we alter our seeding rate is to try to maximize yield produced per acre farmed. Some advantages with going with a lower seeding rate is you have lower plant-to-plant competition between the plants within the row. The distance from one plant to another tends to be greater as compared to at a higher plant density. A higher plant density, though, may help you arrive at canopy closure sooner than if you're using a lower seed density. But again, much of our seeding rate decisions revolve around our yield potential within our environments. When we think about the yield response types that we can see with our given environments, there's generally 4 that we tend to see in corn production. The 2 types shown on this slide are linear in nature, meaning that as seeding rate on the x-axis increases, grain yield on the y-axis also will either increase at a steady rate or decrease at a steady rate, leading to either a linear positive relationship or a linear negative relationship. In this case, with a linear positive relationship, our optimum seeding rate is probably going to be on the higher end of the values tested. As compared to a linear negative relationship, our optimum seeding rate is more likely to be on the lower end of the values tested in that assessment. Often we see quadratic type relationships with regards to corn seeding rate and grain yield, again showing on the X and Y axes. Occasionally, yield will increase to the point where we have our optimum yield, which is the peak of the curve. And then when seeding rate exceeds the optimum, yield tends to decline, giving us this quadratic type relationship. In other environments, we may see an increase that shows a quadratic type, but then beyond a certain point, yield doesn't change. We don't get the decline that we'd get with a quadratic relationship. Instead, yield levels off with additional seeds added per acre. And this type of relationship would be called a quadratic plateau type relationship. Recent work from Acefa et al. In 2016 has shown that sometimes the relationship that we observe may be related to the yield potential of the environment. In the figure shown on this slide, in panel A, we're looking at a low yield environment or environments that yield less than 110 bushels per acre. In panel B, we're in a medium yield environment ranging from 110 to 160 bushels per acre. In panel C, are high yield environments or 160 to 210 bushels per acre. And environments with very high yield, or those that exceed 210 bushels per acre, tend to fall into panel D. And what's interesting to note is that in panels A and D, the relationship may appear to be linear, either as negative or positive respectively, potentially could be quadratic in nature. In a high yield environment, we tend to see more of a quadratic type relationship or a quadratic plateau type relationship. So this information was gathered from 124,000 observations from 22 states across the United States to develop these panels. And so this is a very robust data set, but I think this does a very good job at illustrating how yield potential may factor into how plants respond to changing seeding rates. When we think about how these patterns related to seeding rate and yield are developed, we ultimately have to look back at how yield is determined, which essentially is a measure of kernel weight per acre. When we change the number of plants per acre with increasing seeding rate, we may be increasing our plant number, but what tends to happen is competition from one plant to another tends to increase, and ultimately fewer kernels or kernels of smaller size are produced as a result. And that's what we see in this panel here. What we're seeing is seeding rate in 1,000 seeds per acre increasing on the x-axis. And on the y-axis, we have grain yield, as denoted by the blue squares, or per plant yield, denoted by the orange triangles shown. For each 1,000 increase in seeding rate, we see an overall increase in yield of 0.6 bushels per acre. But when we look at the per plant yield is decreasing by 3.6 grams per plant per 1,000 seeds increased. And ultimately, the rate of change for the per plant yield and increasing seeding rate value will ultimately determine the yield response curve, whether that exists as a linear relationship, quadratic, or quadratic plateau. To illustrate the effect of seeding rate on corn kernel production, I have two ears that have been imaged and stitched together to form a 3D model showing a typical ear harvested from a 24,000 plants per acre stand and a 44,000 plants per acre stand. Some of the things we can notice is that the ear girth tends to be a little bit greater than what we see at the 44,000 plants per acre. Additionally, the number of kernels produced per row is also much fewer for the higher seeding rate as compared to the lower seeding rate. So the per plant kernel production tends to be greater at lower seeding rates compared to higher seeding rates. Another factor that contributes to yield is the kernel depth, which can contribute to the weight, and that may also be affected by our seeding rate. When we think about our yield response curves that can be seen with our different yield potentials in our different environments, we also have to acknowledge the fact that the response to seeding rate in corn hybrids has also shifted over the last 30 years. In a recent paper published by Acefa et al. In 2018, they reported that the optimal seeding rate for modern hybrids has increased over time, and that ultimately the response to seeding rate curve has flattened with modern hybrids, which ultimately can reduce the yield penalty from overseeding. To illustrate this, I've pulled figure 3 from their paper, in which they report data collected from 23 states plus 3 Canadian provinces that was collected from 1987 through 2016. And what can be seen in the first panel is that grain yield on the y-axis and hybrid release year on the x-axis has shown that yield has increased over time with these hybrids. But if we extrapolate over to look at seeding rate and its effect on the different hybrids from the different eras, we see the oldest hybrids shown at the bottom here. And essentially, the seeding rate was slightly lower than where it is for optimizing yield for hybrids produced from 2012 through 2016. So this increase in optimal seeding rate has been observed. The other component that's changed over time is how yield declines when seeding rate exceeds the optimum. The yield penalty tended to be much higher with hybrids released in the 80s and 90s as compared to those released more recently. So the penalty from overseeding has become a little less dramatic with modern hybrids. In Ohio, we looked at seeding rate response for 84 different trials conducted throughout the state. And what we observed was that the response model varied by site and year and alternated typically between the linear, quadratic, and quadratic plateau type relationship. The panel shown on the right shows increasing seeding rate in 1,000 seeds per acre and estimated return to seed. So these analyses not only factored into the agronomic optimum, but took into account the cost of seed and cost of grain and determined the optimum seeding rate when those factors were also included. The economic optimum range for Ohio environments had a wide range all the way from 18,000 to 44,000 seeds per acre to optimize productivity in those environments. The response functions across these Ohio environments were, for the most part, relatively flat, which ultimately could make optimization of seeding rate within an environment a challenge, especially if that optimum seeding rate may change from year to year. Some considerations that may need to be taken when looking at seeding rate that involve other management decisions include hybrid selection, planting date, and row spacing. I'm going to focus first on the impact that hybrid may have on seeding rate decisions in Ohio production environments. In work that was done at Ohio State University, there was multiple trials conducted that compared short season corn hybrids ranging in maturity from 102 to 105 days to full season hybrids, which ranged from 108 to 116 days. These trials were conducted across 2 Ohio locations for 5 years, and within each year, there were 5 hybrids that made up the short season and 10 hybrids that made up the full season for comparison. Across all of these environments, years, we observed that short season hybrids tended to have a slightly greater optimal seeding rate as compared to the full season hybrids. Across all of these trials, it was about 3,900 seeds per acre greater for short season hybrids, which was about 11% increase compared to our full season hybrids. Another study that was conducted at Ohio State suggested again that short season hybrids may require a slightly greater optimal seeding rate as compared to full season hybrids. In this case, 2 short season hybrids were compared to 2 full season hybrids across 3 sites in 3 years. In general, short season hybrids required 1,600 more seeds per acre to optimize seeding rate compared to the full season hybrids, which was an increase of about 4%. If we look at the larger scale paper from Acefa et al. In 2016, we can see that similar trends were observed for latitudes that are relevant to Ohio, ranging from 35 to 40 in the left panel and 40 to 45 in the right panel. In general, the longer season maturity hybrids tended to optimize their seeding rate at a lower value compared to the shorter season hybrids, both in the southern portions of the state and also the northern portions of the state. Interestingly, the same researchers observed that there may be an interaction with hybrid maturity and yield level, which could explain some of the variation we saw in the yield responses that were reported. Again, panel A is showing a low yield environment, panel B is showing a medium yield environment, C is a high yield environment, and D is a very high yield environment. In panel A, many of the hybrids of the early season tended to show more of a quadratic type relationship, whereas The longer season hybrids tended to show a negative linear relationship, suggesting that again, longer hybrid maturities will optimize their population at a lower value. That trend tends to hold true with regards to that relationship in both B and C, which are the medium and high yielding environments. Another consideration when thinking about hybrid and seeding rate interactions is the susceptibility to damage that may be incurred. In some cases, with increasing seeding rate, we may experience an increased susceptibility to stalk lodging. In some of our past work looking at both short season and full season hybrids, we saw a 4 to 7% increase in stalk lodging when seeding rates increased by 1,000 seeds per acre. Some of this susceptibility may be due to changes in stalk characteristics. When we examine the stalk diameter of these plants planted at 24, 34, or 44,000 seeds per acre, we notice a decrease in the diameter going from a low seeding rate to a high seeding rate. Thinner stalks may ultimately make these plants more susceptible to stalk lodging, which can make harvest a little bit of an issue. When wind damage occurs in the late vegetative stages, we do see that there is an interaction with seeding rate with regards to plant susceptibility to root lodging. When windstorms come through between V12 and V14 in Ohio environments, we observed an increase in root lodging damage with increasing seeding rate. However, susceptibility to green snap seemed to be unaffected by the seeding rate relationship. So in summary, when we're thinking about hybrid selection, the data that we looked at suggests that shorter season hybrids generally have a slightly higher optimum population as compared to full season hybrids in the same environments. Let's look at planting date next. In general, when planting is delayed beyond early May, we tend to see a decrease in yield production. On average, this is about 11% when planting is delayed until June. However, the loss can increase with delayed planting, as shown in the panel on the right. Planting date is shown on the x-axis, and relative yield is shown on the y-axis. When planted in late April to early May, yield is roughly 100% of the maximum. Beyond that point, yield starts to decrease, and when planting is delayed until late June, yield drops fairly significantly, down to 52% of what it could have been had it been planted in early May. One thing to note is that June plantings may be less damaging in northern environments, where in some cases, June planted corn may outyield early May planted corn due to different environmental conditions. In trials done at Ohio State University at the Western Agricultural Research Station and the Northwest Agricultural Research Station, it was observed that seeding rate responses were similar for these hybrid types regardless of planting date. In general, at these sites, the western site, seeding rate tended to range from 39 to 42,000 seeds per acre as optimum, but we did notice a decline in yield with delayed planting. Similarly, at the Northwest Research Station, seeding rate increased marginally for our drought-tolerant hybrids that were being evaluated, but decreased for the conventional hybrids when planting was delayed. Regardless of hybrid type, yield was decreased with June planting. So in general, seeding rates may shift, but the trends are not consistent. It doesn't necessarily mean more seeds are needed if planting is delayed. So in general, when we consider planting date with seeding rate interaction, at this time, we're not suggesting an adjustment in seeding rate be made. Let's proceed to look at row spacing. When looking at trials that were conducted in Ohio and Pennsylvania, comparing 30-inch row production to 15-inch row production for modern corn hybrids at seeding rates ranging from 35,000 to 45,000 seeds per acre, we observed a very limited interaction of row spacing and seeding rate, with only one location experiencing a significant interaction. At the South Charleston location, optimal seeding rate in 15-inch row production was measured at 45,000 seeds per acre, whereas the optimal seeding rate was identified as the medium rate of 40,000 seeds per acre in South Charleston that same year. Most other sites did not exhibit an interaction with seeding rate and row spacing. And these results are fairly consistent with other research produced from the Midwestern states, in that seeding rate generally tends to be optimized in a similar way for narrow row production as compared to wide row production. To summarize, row spacing does not necessarily impact the need to adjust seeding rate. One final consideration with regards to seeding rate and management practices is the thought of nitrogen application. In work that we've conducted in Ohio, we've noticed that nitrogen rates do not need to be increased with increasing seeding rates. In a recent study, there was 8 site years that examined corn following corn and corn following soybeans planted at 30,000 or 40,000 seeds per acre. Across these 8 environments, 7 of the 8 site years showed no interaction with nitrogen rate and seeding rate. Only 1 site year showed an interaction, and it was in the corn after corn rotation. But in general, nitrogen rate should not need to be increased with seeding rate. This module has covered what the recommended corn seeding rate ranges are for Ohio production environments, how yield can be impacted by seeding rate, and how other management decisions impact seeding rate. In summary, most Ohio environments needed a final stand of 31,000 to 32,000 plants per acre to optimize yield production. Higher yield environments tend to have a higher optimum stand to maximize yield, 34,000 plants per acre or greater in some cases, whereas lower yield environments will have lower optimum stands to maximize yield, generally in the range of 24 to 26,000 plants per acre. Regardless of seeding environment, you'll need to adjust seeding rates to reflect for expected loss to ensure that the seeding rates will result in the target final stands. Yield responses of corn hybrids to seeding rate can vary by environment, but tend to exhibit patterns that appear as linear, quadratic, or quadratic plateau. These also may be related to yield potential of those environments. Seeding rate adjustment may be needed based on hybrid selection, particularly related to hybrid maturity. Short season hybrids tended to achieve a maximum yield at 5 to 10% greater seeding rates than full season hybrids in comparable growing conditions. Planting date tended to have minimal impact on seeding rate, and row spacing had minimal effect on optimizing seeding rate. Finally, nitrogen rate does not need to increase with increasing seeding rate, and we suggest producers still utilize the maximum return to nitrogen calculator to determine an optimum application rate for their production environment.